Now, yesterday we did just the oxidation numbers. Today I want to talk about, we're going to do Swift double period. So I'll first do the oxidation reduction, what they each are, and how you can identify them. And in the homework, you'll be identifying the oxidation, the guy who's undergoing oxidation or reduction, and what's called the oxidizing agent and the reducing agent. All right, and I'll show you an example of a reaction that we've seen before many times, actually, in Chem 1. All right, but we're going to actually diagram it out and show you why this particular reaction is a redox reaction. Okay, take a look here. I've got some silver nitrate. You've seen this, used this before a bunch of times.
Very expensive.
It is very expensive, and what does it do to your hands?
Right.
Turns them brown. Okay. If I take some silver nitrate and I add some copper to it. Actually, you saw this one underneath a microscope last year.
Oh, is this where the silver reacts with the copper? And
it makes silver.
Yeah, it makes silver.
Yeah.
Exactly. And you guys already figured it out. But I'll throw it in here anyway. And I have a thing here. I'll just put some copper in here.
Is it like real silver that you can like make stuff with?
Yes. But as somebody asked,
Is that right?
yeah, and you can make something with that. Somebody asked, well, is it worth, because you can make money doing this? Absolutely not. I told you the other day, a bottle of, it was bigger than this, it was 500 milliliters. This is probably about 125 milliliters. A 500 milliliter bottle of just 0.50 molar silver nitrate costs $125. So you can't get silver from nothing. I mean, obviously, you have to buy that bottle first, and then even if you wanted to make the silver, it would be kind of a waste of money. All right, at first it just looks like copper in there, but in a little bit we'll come back, we'll look at that, I'll pass it around, and you'll see that it will look different. It'll look, you'll see silver on there. I'm going to move that out of the way so we can get our notes, and we're going to use that as our example. So what's happening in an oxidation and reduction reaction? Oxidation. Oxidation is when you have a guy's charge within that equation from one side to the other becomes more positive than it was before. Okay? It's an increase in oxidation number. And that corresponds to, if it's increasing its charge, it must be losing electrons. Okay? So that's the definition of oxidation. Not every equation you see is an oxidation-reduction reaction, as I'll show you in a second. All right, but let's talk about, before I get to that, before I show you an example of one that's not a classic example, let's just, what do you think reduction is going to be without me telling you? Yeah, it's going to be a decrease in the oxidation number. And, of course, that corresponds with a gain in electrons. Now, already we see a problem, and it's going to be a problem for the identification of what's going on here in the homework tonight and on the test. Because our test is just equations, but I am going to ask you to label what each thing is. Like being oxidized or reduced, the oxidizing agent or the reducing agent. All right, and already we see a problem with this. The guy who's being reduced is actually getting more of something. You're actually adding something to a guy who's being reduced. How come? Who can explain that? What's the logic behind giving it something and yet calling it reduction? It has more electrons now than it had before. How has it been reduced? Yeah, the charge, because what's the charge of an electron? Negative. Giving a guy more electrons makes him more negative. He has more particles, he has more electrons, but he's been reduced, not in the fact that he has fewer particles, but in the fact that his charge is now lower than it was. Okay? So that's the one. Already we're seeing some confusion. We're going to see even more of it by the time I get down here. All right, but let's get this example right now. This is the one we're going to be doing right there. I just put copper into that test tube, which had silver nitrate in there. And I made copper nitrate, which, by the way, you won't notice this as much. All right, but if you do look at this at the end of the period, you'll notice that the solution will be turning slightly blue, a blue tint to it. That's from the copper nitrate that you formed as well. The more obvious thing, of course, will be the silver. And if we look at it right now, you can already see the silver starting to form. All right, it no longer looks like copper, except at the very top where it's above the water level. Now it looks like gray colored. And by the time we're done, it'll look even shinier. And we looked at that under the microscope, under the crystal lab, if you remember. Okay. Now, let's do the learned yesterday how to do the oxidation numbers for everybody, and then you can tell who's actually changing. So let's do the oxidation numbers for everybody over here. What's copper by himself?
+1.
Copper by himself is 0. Anybody by himself is 0. And why would you say +1 anyway? Copper is a guy on the periodic table who's in the middle, and he has multiple oxidation states. You'd have no reason to say +1. All right, silver, if it was silver by himself, I could see that because that is common. His state is commonly +1. Copper could be +2 or +1, and it depends. Now look over here. Here's a case where I could use my knowledge of polyatomic ions, all right, and do this separately if I wanted to. What do I know the nitrate ion to be from the sheet?
-1.
-1. What does therefore Ag have to be? +1. But I'm not okay with that. I still have to do the charges of the guys inside because you're going to find very soon when we do these next period that a lot of times even inside of here they're changing. So the oxygen is always -2. What does nitrogen have to be in this case? Everybody agree it's +5? Okay, there's two ways you would know that. You could realize that the nitrate itself is a -1, so 3 times -2 is -6, so n -6 equals -1, n would equal 6 -1, or a +5. Or, now knowing that silver is +1, you could have done it all that way too. But either way, that's correct. It's +5. Now, what's happening over here? Again, using your knowledge of the nitrate ion is -1. What do you know copper has to therefore be? +2. And by the way, I'll give you another hint here. When you go to do these, you'll save yourself a little bit of time if you realize that if a polyatomic ion does not change between both sides, then that means the charges inside couldn't have changed. All right? So it's a -2 here and a +5 again here. Okay?
One quick question.
Yeah.
You do not have to use the 2, correct? But if you do it this way, you do not have to use.
Right. If I'm just looking at nitrate separately, I don't use any subscripts outside because there was no subscript outside of that one. It's the same thing. All right. But if I'm trying to figure out copper, of course I do. 2 times -1 is -2.
Gotcha.
All right. Silver by himself, what is he?
0.
0. Okay. All right. Now, I'm going to talk about how each of those guys is changing, but in a second. First, I want to show you how well. Is every reaction of one of the homework problems going to ask you, identify the oxidation reduction reactions. All right, if I give you a problem like this, one of the classic precipitate reactions we just did last week in the lab, we mixed the two guys together after a long lab, and it turned a white precipitate. That was this. We took salt, NaCl, don't write this down, plus AgNO3, silver nitrate again. And we got AgCl plus NaNO3. All right? And that was a precipitate. This is the guy that precipitated out. But that's not an oxidation reduction reaction. +1, -1, +1. That whole thing is -1. He's a +5, -2, +1, -1, +1. Same thing. Nobody changed. Sodium's +1 over here. He's +1 over there. Silver's +1 over here. He's +1 over there. No change occurred. But in this case, look what happened. Yeah, Cu was 0, now he's +2. Silver was +1, now he's 0. Okay, those guys changed. All right, so I need to identify what they underwent and then tell me something else about them, what they're called. Okay, watch. First, for copper. All right, copper went from 0 to +2. Was that oxidation or was that reduction? Was he oxidized or was he reduced? Everybody agree he was oxidized, right?
Yes.
And silver went from +1 to 0. What happened to him? He was reduced. Now here comes the next confusing thing about this. Okay? And it's the last I'm going to do today. This is not a long class. All right? And then I'm going to give you some time to work on the problems before I start the next stuff. I will start the next stuff probably before the end of this period because the homework for tonight is very, very minimal. Versus the homework for tomorrow, that next period is much more, no one finished in the other class. I'm not going to be here tomorrow. You're going to have a worksheet and whatever homework you didn't finish to work on. You only have a single day of a double, but believe it or not, even the double period probably won't finish it. All right, I have a training thing tomorrow. But here's the next confusing part. If it wasn't bad enough that I had to remember that reduction means you're actually gaining electrons. It's even worse for this. Copper was oxidized, but he's called the reducing agent. Silver was reduced, but he's called the oxidizing agent. Now, let me see if I can explain to you why that's the case. If you think about it, to be oxidized means that he did what? He lost electrons. So here he is, copper, giving up some electrons. Here's these 2 electrons being given. Where do they go? Where do you think they went? They went to silver, right? They went to silver. So he is the agent responsible for reducing silver by giving him his electrons, and vice versa. Silver took those from him. So he's responsible for oxidizing copper by removing those electrons. Oh, and by the way, do you notice something? One last thing before I leave this alone. Copper lost how many electrons to become Cu plus 2? But silver only gained how many electrons? From plus 1 to 0? 1. What haven't I done to this equation yet? I haven't balanced. And that's what we're going to spend the rest of the week doing, balancing these kind of equations. This guy is about as easy as it gets. I've got, let's erase all of this stuff. I've got 2 nitrates here, so I'll put a 2 in front of there. Gives me 2 silvers, I'll put a 2 in front of there, and I'm done. And you should do that. All right? But you guys remember, those of you who had this last year, not all of you did. Dayton's not here, he didn't. Jesse didn't. In your class too, some people didn't. You guys who were here last year, remember that we're going to have coefficients of 18, 20, 30, 40. All right, I don't think we had any in the hundreds. We might have. But we definitely had multiple double-digit ones in the same equation, and more than just 1, 2, 3, 4 compounds, rather 4 or 5 on one side, and then 4 or 5 on the other side. I mean, it was that hard. All right, and you're going to find that you can't just balance them by inspection. You're going to have to learn the system. I'm going to teach it to you tomorrow. All right, but tonight the homework is, I think I have it on here, I'm not sure. Yeah, I do. 43 to 46, page 170. Now you will not get them all finished right now before I start the next thing, but I do want to start the next thing because that's the harder problem.